Welcome to this lecture number 35 of the course Computational Hydraulics. We are in module 3 groundwater hydraulics. This is unit number 5, unsteady flow in unconfined aquifer using finite volume method. In our last lecture class, we have discretized the unsteady flow equation for confined aquifers using a finite volume method. So, what is the learning objective for this particular lecture? At the end of this particular unit, students will be able to solve unsteady two-dimensional groundwater flow in unconfined aquifer using finite volume method. Problem definition to solution will be utilizing H, X, Y, T, because in unconfined aquifer flow, the flow will consider only in horizontal direction. So, in this case again will be utilizing this problem definition, mathematical conceptualization, domain discretization, numerical discretization. Obviously, in this case we will be utilizing finite volume method, but the main difference with the confined aquifer flow is the nonlinear equations. In case of our this unconfined aquifer flow, we will be utilizing nonlinear equations, and now solution approach will be different compared to our linear equations that we have utilized for confined aquifer flow. So, problem definition, I am not going to the details of the problem definition. Now, in this case again our system is homogeneous isotropic system. Boundary conditions are same like our previous confined aquifer flow, but only difference is that we are considering it as unconfined aquifer flow. In confined aquifer flow, we need to define storativity, but in unconfined aquifer we need to define specific yield. Obviously, transmissivity is required. We will define the hydraulic conductivity in terms of Kx, Ky in isotropic system. Kx will be equal to Ky in this case. Let us define our two-dimensional problem. In our confined aquifer problem, we have utilized this equation del H by del T and del 2H by del X2 plus del 2H by del Y2. Now, in this case we have extra term this H, and because of this H the equation is nonlinear in nature. Now, let us consider that Sy specific yield is 0.25 and K is 20 meters per day. Obviously, in this case Kx equals to Ky equals to 20 meters per day. Now, we need to see how we can solve this using our finite volume approach. Initial condition, again the conditions are same like our finite difference approach or finite volume approach that we have utilized for our confined aquifer system. Domain discretization, again we will have interior nodes. So, again one for interior node or a interior I should say interior cell plus boundary cell will have 4 and corner cell will have 4 conditions. So, all total we need to consider 9 conditions for this problem. Obviously, this is Lx and Ly, this is y direction, this is x direction. Now, in finite volume method, governing equation is integrated over the element in space and time interval to form the discretized governing equation. Now, in this case we have the space and time derivatives. This f vector is fx fy, obviously f vector if we consider this is nothing but fi plus fy j, where I and j these are unit vectors in corresponding x and y directions. So, this is fx is this quantity. So, initially this was the case where kx h del h by del x plus this is y ky. Initially let us consider that our kx ky are different and those are varying with x. So, we will formulate the general problem and during solution we will consider kx and ky, those are having equal values. So, this is nothing but fx plus fy so we can write this as divergence of f. Now, if we write it in terms of divergence of f, again we can utilize Gauss divergence theorem for the first term on the right hand side, and we can use the integration concepts for other terms to get the final discretization. Now, the first term on the left hand side, this is Sy del h by del t. If we consider that no variation of h within this omega p volume, we are considering that omega p, this omega p is the volume in this case. So, within this omega p there is no variation of h, we are considering constant value for this one. Now, with this consideration, if we further write this, so this will be nothing but Hp into del omega p, which is the volume for this cell. Now, we need to integrate it. So, obviously, if we integrate it over time period or time interval, we will get something. So, what is that? So, we will get this Hp L plus 1 to L, because L this corresponds to T and L plus 1 this corresponds to T plus delta T. Now, if we use this, finally, we will get that our del omega p, this is nothing but del x del y and u net value on the other direction. Or we are considering 2D volume only in this case. So, that is why it is del x into del y. Now, let us consider the component or first component on the right hand side. So, this is the divergence form, again divergence form of this one. As we have discussed that area is always outward positive. If area is outward positive, then this is nothing but del y I, this is minus del y I, this is del x j, obviously negative sign will be there. On the upper side this will be del x j and this is p h cell. Now, for this cell if we consider that f dot dA from our Gauss divergence theorem. So, f dot dA, this component for all faces, that means we need to consider this east, north, west and south, these faces here. So, for all faces if we consider this quantity dot area for eastern face, obviously this will be positive. In this case AXE, this is nothing but del y, this is AXW, this is again del y because negative sign is already there. So, we should not consider this thing. So, AY north again del x, y south again this is del x in this case. So, we have discretized the second term in terms of these derivatives, east, west, north, south and del t will be there. Now, if we consider uniform grid system as I have discussed, so this will be the case. And source term, if we consider the source term, obviously this is valid for cell value, W is valid for cell value. So, obviously del x, del y, del t, they should be multiplied here. Now, in compact form, if we combine all terms, we can get this on the left hand side, this is the thing, and on the right hand side del y will be multiplied with eastern and western phase, del x will be multiplied here and del x, del y, del t on this side. So, if we see the case for interior cell, now interior cell east face, this is important. East face, we already know that del h by del x at east face, we can write it in terms of h e l plus 1 minus h p l plus 1. This comes from the concept of implicit scheme, because we are using L plus 1 index for time, and spatial derivative we are utilizing the concept of finite difference. Now, this is H e. What is this H e? H e is the age value at the face. Now, how to calculate this age value at the face? So, what is the ready-made approximation? Ready-made approximation is that if we can consider this H e plus H p by 2, that means the average value between this P and E cell, that can be considered as our phase value for the east phase. So, this is our phase value and this is the derivative value multiplied by K x E, that means hydraulic conductivity at the face. Now, we are considering that we have homogeneous isotropic system, but in this case we are considering generalized formulation. So, we will simply use K x instead of this K x E. Now, let us see what is the situation for west phase. West phase is again similar. We will consider H w as H p L plus 1 plus H w L plus 1 divided by 2, and this derivative we already know that del H by del x at western phase H p minus H w divided by delta x. So, this is the average value, this is the derivative. Now, we can write the east phase and west phase like this. Now, if we have northern phase again we can discretize or approximate this H n in terms of H n H p and the derivative as H n minus H p by del y. Now, if we have southern phase, for southern phase we have H s is nothing but H p and H s average and H p minus H s divided by del y. So, with this we can further simplify our compact form of the equation. On the right hand side, interestingly we are getting this square terms H e minus H p square, H p minus H w square, H n, H p, H s, all square terms. So, this is one nonlinear equation. Now, in compact form what we can do, we can transfer this S y on the right hand side and del t we can include here. So, del x square obviously in this case will get this parameter kind of thing multiplied by 1 by del x square, also k x del t by 2 s y this should be multiplied by 1 by del x square. Now, we can simplify it. So, if we further simplify this thing with the approximation that k x del t by 2 s y del x square, k y del t 2 s y into del y square, we can write it in approximate form. So, now approximate form is this alpha y into h s square plus alpha x into h w square minus 2 alpha x alpha y. These are coming from here because coefficients 2 for alpha x, 2 for alpha y, and 1 which is coming from this side. This is minus h p L plus 1. This is not square term. Remember that this is not a square term here, but this h p is a square term. Now, another term will be there, alpha x h e square, alpha y h n square. So, on this side we have all known quantities. Now, this is the discretized form for interior points. Now, if we have nonlinear equation, obviously we need to solve it using some nonlinear technique, and one of such technique is Newton-Raphson. In Newton-Raphson, we need to define the Fm or our function, which is a function of h L plus 1, all unknown quantities. So, I have written all left hand side terms here and transferred this right hand side to the left hand side and equated this one with 0. So, this is my functional form or function form. Now, I need to calculate the derivative term or elements of Jacobian matrix. So, to calculate the elements of Jacobian matrix, so I need to take derivative of Fm with respect to Hs, which is 2 alpha y Hs, it is directly coming from here. Now, next one is Hw, which is coming from here. This is 2 alpha y Hw L plus 1. Then comes this Hp, which is again minus 1. Minus 1 means because in this case there is no coefficient available. If we simply take derivative here, we will get minus 1, minus 4 because 2 is already there, the square term, this is 2. So, 4 alpha x alpha y into Hp, then He on the eastern side we have 2 alpha x into He, 2 alpha y into Hn, this is there, and this is our right hand side term. Obviously, this is a constant term for function calculation because we are considering this unknown at L plus 1 level. So, with this if we proceed, then we can construct one row of the Jacobian matrix. Now, for all cells, that means if we have m cells, MC and n cells in y direction, this is in x, this is in y direction. For MNC into MCNC, this will be the size of the Jacobian matrix, and we will have pentadiagonal structure of the Jacobian matrix, because we will have P term, W term, E term, N term and S term. So, obviously, no other term will be associated with the central point or point P. So, obviously, we will get this P, this is for our other ones on the right hand side, which is eastern one, this is western, and this is our northern, this is southern. So, like this we will get the terms for interior points, these points will get from these equations. Obviously, this will be J S. So, S means this one, this is W, W is this one, P is this one, E is this one, and N is this one. So, for all interior nodes, that means for all interior nodes we need to calculate this, but this is the node number including the boundary nodes. For boundary nodes we need special treatment. So, let us see how we can utilize the concept for boundary nodes. Now, we have left boundary. Left boundary, this discretization is exactly same as we have utilized for confined aquifer system, because the derivative term will be same, but we need to multiply H W or value on the right hand side. This is our original equation which is in discretized form. On the right hand side, if we consider eastern phase, we can directly use the form that we have utilized for interior nodes. For northern phase, again we can use the same thing. For the southern phase also we can use that one, but for the western phase we have something different. This is for applicable for derivative, then we need to multiply HBW, which is the height at the face. Height at the face is equal to specified value for this case. So, if we have specified value, then we can directly use that, because that is a known value. So, if we simplify this, again we will get terms with HS, HP, HP, HE, HE and HN. In this case, we do not have any HW term, because for HW term, because we do not have W cell in case of left boundary. And the right hand side we have this 16/3 alpha x BW, this is the first term. We need to transfer this on the right hand side, and again our approximation is based on this parameter alpha y equals to del t. This is nothing but alpha x equals to del t into k x, and this is S y 2 into delta x square. This is alpha y equals to k y del t divided by 2 S y del y square. So, further if we discretize this or if we write it in terms of functional format or a function format, then we need to transfer the terms on the right hand side to the left hand side, so that we can write it as equal to 0. On the left hand side, interestingly we have 2 alpha y which is coming from these two, but only 1 alpha x which is coming from here, and the coefficient this 6 alpha x, this is coming from here 3 into 3, this is 3, and from that 3 because we have considered this alpha x equals to this one, we need to consider this. This is 2 into 3, that is 6 here, 6 alpha x, that is coming here. Now, on the right hand side we have this alpha x, whatever is there on the left hand side, and this is from the right hand side directly coming. Now, we have this derivatives h s, which is corresponding to this one, then we have h p or j p. J p is minus alpha 2 alpha x and 2 alpha alpha x plus 2 alpha y. This is 1 plus alpha x into h b w, and j e again it is coming as 2/3 alpha x h b w, and h e again there is another term with a square, and there will be northern term or northern boundary. So, in this case obviously we have a j w m, this is equal to 0. So, we do not have this term in our Jacobian matrix. Now, if we consider our right boundary, again the discretizations are exactly same as our confined aquifer system, but in the next page where we have utilized the equations are different. So, for eastern face this is the change, and this is the only change required, because other terms these are exactly coming from the interior node discretizations. So, in this case this B term, which is again specified thing, this is coming here on the right hand boundary. This 3 term, this is coming here as 6 alpha x. So, we have this thing for our case where we are getting all terms except this h e, because there should be no h e here, only h p, h w, h p, h w, h s, h p, h n, and all known values are there on the right hand side. So, alpha x, alpha y, alpha x, this is coefficient of h s, h w, and extra emphasis on h w here, and 2 alpha y, this is coming from this one, but only 1 alpha x, this is coming from here. Now, this is a functional form, this is our right hand side, this is left hand side, this is our right hand side. Now, if we take individual components of the Jacobian matrix or elements of the Jacobian matrix, we will get like this. This is 2 alpha y h s, j w, this is 2 alpha x, again 2/3 h b e, this will be there, h p, which is exactly same, 2 alpha x plus 2 alpha y H p, and finally we have H n, but no H e, or this case this is 0. We should remember this should be 0 in this case, because we are considering right boundary. Now, if we consider our top boundary again this point is important, because we need to apply this 0 condition on the derivative, and if we apply this condition, so obviously in this case on the northern boundary this is 0, and as we are considering other derivatives similar to interior points, these are exactly same like interior points, and we will get like this. So, obviously 2 alpha x, because 2 p terms are there, and 1 H p L plus 1 which is coming from here, and H p L which is coming from the which is there on the left hand side. Now, I have there in the right hand side, which is the known quantity. Now, if I write it in function form, this is our left hand side, this is right hand side. Now, derivative for H s H w, then H p, for H p we have -1, then 2 alpha x plus alpha y into H p, this is there, and H e, obviously there should be no J n m term, this is 0 in the Jacobian matrix. Now, if we have bottom boundary, again for bottom boundary we need to apply this 0 condition, other terms are same like our interior points. Now, if we apply the same thing here, so this is 0 for other faces, we have these forms. Now, we have 2 alpha x coming from here, and alpha y only one term here, and again H p L plus 1 which is coming here, and alpha x E n w, but no H s L plus 1 term in this case. So, we have left hand side, right hand side, and w, obviously this is 2 alpha x into H w L plus 1. Now, J p is -1, this is 2 into 2 alpha x alpha y H p L plus 1, J e is 2 alpha x directly coming from here, J n, this is 2 alpha y H n L plus 1 from this one. Now, we need to consider this northeast or northwest corner. Northwest corner, northern side we have impermeable boundary, obviously we need to put the 0 condition, and the western boundary we need to put this Dirichlet or specified boundary condition. So, if we apply that, in this case interestingly we do not have any W term, only E, P and P S, that means no northern term or H n L plus 1 or H W L plus 1 here. So, only one alpha x is coming here. From here we are getting 1 alpha y. Again from here I am getting this 6 alpha x H B W, and we need to transfer this on the right hand side. In this case this alpha y h s square, this term is there. So, now similarly we can write it in function format. So, we have H s, this is J s, J s is 2 alpha y H s L plus 1, P is this one 2 alpha x plus alpha y, this is 2 by 3 alpha x H B W L plus 1, 2 alpha x H E L plus 1. So, we do not have J W M, this is 0, and J N M, this is 0. So, in Jacobian matrix you will not find these two terms. Now, if we consider our northeast term, if we have northeast, so northern side we have 0 and eastern side we need to specify the specified boundary condition. Now, this is exactly same as our specified boundary condition, and northern side we need to put the 0 condition, and this is the condition that we have utilized from the specified boundary condition. Now, we will get H s, H w, H w, H p, H p, that means no n L plus 1 or E L plus 1 term here. So, if we consider our function format, again 2 alpha y H s, this is coming as western. So, from western side 2 alpha x H W L plus 1 and 2/3 alpha x H B L plus 1, this is there. This is J P and this is 1 plus 6 alpha x B, this is directly coming from here, and this is 2 alpha x plus alpha y, this is the term that is coming from here. Now, we do not have any J E M, that means this is 0, then J N M, this is again 0. These two terms are 0 terms. Now, the southeast corner, on the southern side this will be impermeable. So, obviously, this will be 0. On the eastern side we have specified boundary condition. So, for specified boundary condition this is 0 on the southern side. On the eastern side we have a specified condition which is directly coming from here. So, we will have western term or H W term H P, H P, H N. So, no H s and no H E term here. Again we can get equivalent function form. So, from this J W, this is directly coming as 2 alpha x H W L plus 1, 2/3 alpha x B H P J P, this is coming as 2 into alpha x H P L plus 1, and this term is there 1 plus 6 alpha x b, and on the northern side we have 2 alpha y, this h n l plus 1, and this is our right hand side, which is the known quantity. Now, we do not have any J S m that is 0, and we do not have any J E 0. So, these two terms are 0 terms. Now, if we consider southwest corner, the approach is similar. We need to put 0 condition here. If for southern boundary this is 0, and for western case we have transferred these values and derivatives. So, for western boundary we do not have any H s L plus 1 or H w L plus 1 term. So, directly we can get this discretized form, and this is the function in the form of function discretized form can be written. This is our form, again Jp is coming from here, this is 2 alpha x, this is there, this is 2/3 Bw Hw, 2 alpha x He, 2 alpha x He coming from here, and 2 alpha y Hn L plus 1, this is directly coming. So, we do not have Hs m equals to 0 and Hw m, this is equal to 0. So, this is the condition for our Jacobian matrix. So, we have defined all 4 corners or corner cells and all boundary cells here. Now, we need to see how we can solve this problem. In general form, the governing equation including the boundary conditions we can write like this. So, this is nothing but J s into del H s L plus 1, this is J w, this is J p, J e, J n. So, this is same on the right hand side we have this minus F m, minus F m. Now, in this case we can solve this in through iterative form. This H s can be expanded like this, H w can be expanded like this, H p, H e, H n. And on the right hand side F m, this can be expanded in terms of H s, H w, H p, H e, H n. So, I have changed the color for H s, H w in this case. Why? Because if we consider our problem, then we have central cell, which is our cell P, this is northern, this is southern cell, this is western, this is eastern. Now, during calculation process will start discretizing our governing our domain into number of cells, and we will start our calculation from this point. So, from this point we will move towards this, again we will start from this, again move like this. So, in this case what is happening, first we are solving S, then moving to this direction, and we are coming back here and going to this W cell. So, for calculation of P, the value of S cell and W cell, these two are already updated values available from the calculation process. So, I have marked these values as HSP, HWL plus 1 at pth iteration. This is again pth iteration, this is again at pth iteration, we have updated values available. Now, in this case, further I can just simplify this and write it in final iterative form like this. So, I can consider this value and transfer all other terms on the right hand side. So, I will write this residual. So, in this case residual excludes the central term. So, we have Js, Jw, Je, Jn. Obviously, in this case it is a pth iteration value, it is itself available. So, I have written in terms of pth, and this is p minus 1 level values are available, that is why I have written in terms of p minus 1. So, I can calculate this residual and divided by JPM, that is directly coming from here. So, this is the iterative form. Now, what I can do, I can start the iteration and get the converged value of HPL plus 1. After getting convergence through the iterative format, I can transfer this value to HPL. Then this will become my new old time level value, which is calculated from the future time level, and I can iterate for the time loop. So, initially for any problem we have time loop and space loop. Now, space loop we can solve using this iterative form, and we can update time, and for updated time we can transfer this n plus 1 level value to nth level directly. So, this is our unsteady finite volume 2D finite volume unconfined aquifer implicit iterative format. Now, what we can do, we can solve it using our unsteady equation. Now, in this case again we have M node, M cell, N node, N cell, these are available, and Lx, Ly, these values are available. Time max I have written as 50, HA, HB, HC, HD, these values are directly available. EPS max, this is required for convergence. Sy is 0.25, Kx, Ky, these values are 20 meters per day. Now, for this one we can further calculate Lx, Ly values. This is delta x, delta y. So, obviously, for Lx direction we are discretizing the cells like this. This is equal, but we are starting from this is dx by 2 and we are ending dx by 2 before that. So, in this case for x we are starting from delta x by 2 and running up to Lx minus delta x by 2, and we are getting the cell centered values here. Y similarly we are writing it like this. So, from delta y by 2 we are starting and we are going up to Ly minus delta y by 2. So, that is why I have written it. Now, delta t is 0.5 in this case. So, alpha x, alpha y, we have all values available, HA, HB. So, now if we consider HA, HA is nothing but this value, this corner value. HA is corner level value, this is B, this is A, but we need this value which is not at the center. Now, I can write this as HA modified value and I can write this as HB modified value. So, that I can calculate from here. Similarly, for C and D, C and D, C, in this case C point will be there, this is C, this is D. So, obviously, in this case also we will have that H D modified for this level and H C modified for this level. Now, these are the values directly coming from here. Now, HO, which is old time level, H and P, this is for pth iteration, this is H and P minus 1, this is P minus 1 level. Now, in this case again the approach is same. We are writing the J's, JW, JP, JE, JN terms for interior cell. This is for interior cell and this is FM. Now, we need to calculate DS, which is the difference between HP and HP minus 1 level for DS, DW, DE, DN. Now, in this case we should also calculate the northwest corner, north southwest, southeast corners. So, depending on that J's, JW, JP, JE, JN values will be there. We have to also implement the left boundary, specified left boundary condition, specified right boundary condition, and Neumann boundary condition on bottom, Neumann boundary condition on top. So, after implementing these, we need to calculate this residual. Residual is nothing but minus m and minus Js into ds, Jw into dw, Je, d, Jn, dn. Now, we have not included Jp here. So, this is the residual, residual is residual divided by Jp, and this is H and P minus 1, H and P. and we can calculate this RMSE, and again we can calculate RMSE here, which is the final RMSE, and this is the count. Now, we need to transfer this old values, new values to old value, and we can utilize this for space loop. Then comes the time loop. For time loop, this new value is old value. This is for steady state condition, this RMSE T we need to implement, and obviously we know that for our boundary, we have got values for only internal nodes. That means we have information about these nodes. This is in simple form, this is the information we have, cell centered values. But further we need information regarding these points, so that we can get from the derivative condition. We can equate derivative equals to 0, and Bn and Bs values we can calculate there. Also on the left hand boundary we can directly get the interpolated value from our specified boundary condition. So, after solution, which are green dots, we need to extend our program to get this pink cross and green cross points, so that we can solve the problem for the full domain. Now, if we run this code again, if we run this code, it will take some time, because in this case we need a certain number of iterations for each space loop convergence. In space loop we are solving that Jacobian matrix. If we solve that Jacobian matrix, so obviously here you can see that 744 iterations are required to get RMSE value of 983. So, RMSE value of 983, this is absurd value. So, obviously further 669 iterations are required to get this 133 RMSE value. Now, slowly these RMSE values will decrease, and finally we can get the solution out of this process, and we can get the contour value from this program. And contour value is similar to our finite volume or finite difference solution, but the contour is somewhat different, similar but somewhat different compared to our confined aquifer solution, because we are solving unconfined aquifer problem here. So, you can see that 380 iterations, and slowly this RMSE value is decreasing. This is 2.4, this is 56, and finally we are getting the solution from the program. So, iterative technique we can utilize to solve this unconfined aquifer problem. So, this is all about the unconfined aquifer problem, using finite volume approach. Thank you.